Friends, hello, good morning. In the last class, we have completed under unsteady flow through openings under variable head. We considered two cases when area A is constant, and in the other case, we considered A is variable. When A is constant, you have to express head above the device small h in terms of q in terms of h only. When area A is constant, q should be expressed in terms of h only. When it is variable like a hemispherical tank, we are required to express both area and as well as q in terms of h before integrating. Why? Because area is constantly decreasing as the time increases. That is, as the water is leaving the tank, the head decreases. Okay, the negative sign also in the equation to start with we get because of this. H decreases as time increases. So as to keep the equation in positive, from h1 to h2, instead of h2 minus h1, we write h1 minus h2. That means minus of h1 minus h2. That becomes minus into minus plus h1 minus h2 under the root. Okay. Now further flow around submerged bodies, unsteady flow, we will continue with compressibility. Water hammer, effect of water hammer, remedial measure. How to find the time when the valve is closed gradually or slowly and rapidly. That too for different cases, like when the water is flowing through rigid pipe and when the water flowing through elastic pipe. In case of rigid pipe, whatever the pressure, irrespective of that, it is assumed that the walls will not be get stretched. When we are using the elastic pipe, we are required to consider the elasticity of the pipe material, assuming that because of increase in the pressure due to flow of water, naturally the walls will be get stretched. Therefore, in the first case, rigid pipe, we used to consider only bulk modulus of elasticity of fluid, whereas in the second case, when elastic pipe is used, alone bulk modulus of elasticity of fluid should not be considered. It should be considered as combined or effective bulk modulus of elasticity K suffix E, where K is the symbol we use for bulk modulus of elasticity. The unit is being kilonewton per meter squared or newton per meter squared or pascal under kilopascal. As the system we use, we go for different units that you should always remember. You should not write wrong unit. Okay. Now we will see one by one in detail. First of all, compressibility. The property by virtue of which fluids undergo a change in volume under the action of external pressure is known as compressibility. You are aware, whenever you put some external load on the fluid, it will be get compressed. When you remove the load, it comes back, or it expands to the original volume. It decreases with the increase in the pressure of fluid as the volume modulus increases with the increase of pressure. The variation in volume of water with variation of pressure is so small that for all practical purposes it is neglected. Keep in mind, the variation in volume of water with variation of pressure is so small in practical case or in general that for all practical purposes it is neglected. This you remember. Variation in volume of water is so small that it can be neglected. Thus, the water is considered to be an incompressible liquid. Incompressible liquid. It is a single word, incompressible. Where we assume that liquid also compressible and the effect of the elasticity of fluid is to be considered in case of water hammer. That is the phenomenon of water hammer. That when we come to water hammer, we will make you to understand in a much better way. However, in case of water flowing through pipes, when sudden or large changes in pressure, example water hammer, takes place, the compressibility cannot be neglected. That means in the earlier point we saw that the volume of variation in volume of water is assumed to be so small that for all practical purposes it is neglected, that compressibility. Whereas in water hammer case, it cannot be neglected. That's why I said it is assumed that fluid also, that is water also, flowing through pipe may be considered as compressible. The compressibility in fluid mechanics is considered mainly when the velocity of flow is high enough, reaching 20% of speed of sound in the medium. 20% of speed of sound in the medium. That velocity we call it as celerity of pressure wave, denoted by capital C. Here the word celerity is used just to understand the meaning of the disturbance to travel, not the fluid will travel. Because whenever there is a disturbance occurs in any medium, whether it is solid, liquid or fluid, one fact is true, that it depends. That means the transmittivity of or transmission of this disturbance in such medium is very fast in case of solid, as the molecules are packed together very closely compared with fluids. In case of fluid, it is not so. It takes longer time to reach or longer time to have the transmission of the disturbance in the fluid medium. That's why we consider here celerity instead of velocity. Celerity, that particular word specifically used to understand that it is the flow of disturbance, not the flow of fluid. Please keep in mind. Next point, elasticity of fluids is measured in terms of bulk modulus of elasticity, K. As I have already said, the symbol is K, which is defined as the ratio of compressive stress to the volumetric strain. Compressive stress to the volumetric strain. Compressibility is the reciprocal of bulk modulus of elasticity. Consider a cylinder fitted with a piston as shown in figure. Then this is the original volume. This is the change in volume when you apply pressure P on the piston. This is the cylinder. This is the piston. You can see very clearly. Now if you plot the curve between stress, P is equal to, small p is equal to load applied divided by area of piston and versus volumetric strain. This is dP, change in pressure. This is change in volume with respect to the original volume. Let V be the volume of gas enclosed in the cylinder. The same figure is brought over here also. Let small p pressure of gas when volume is V is equal to P by A, where A is the area of cross section of the cylinder or piston. Let the pressure is increased to P plus dP. dP is the small increment in the pressure. The volume of gas naturally decreases from V to V minus dV, where dV is the amount, small amount corresponding to dP. That's why it is considered as change in volume to the original volume. Then increase in pressure is equal to dP, decrease in volume is equal to dV. Volumetric strain is nothing but minus dV upon V. Change in volume divided by original volume with a minus sign. Negative sign indicates decrease in volume with increase in pressure, that you are aware. Now Bulk modulus K is equal to increase of pressure dP divided by volumetric strain, that is minus dV by V. Here also that figure is carried on. Therefore, bulk modulus of elasticity K is equal to dP divided by minus dV by V. Compressibility is equal to 1 upon K. This compressibility, if you take reverse of it, bulk modulus, you will get compressibility. Is it clear? Yes. Now, water hammer in pipes. In a long pipe, when the flowing water is suddenly brought to rest by closing the valve or by any similar cause, there will be a sudden rise in the pressure due to the momentum of water being destroyed. Because of this increase in pressure, due to the high velocity because of the closing of the valve, there will be positive and negative pressure waves are created inside the pipeline, which will move to and fro, means backward and forward, creating a noise that is known as knocking. Knocking. That is known as knocking. K-N-O-C-K-I-N-G. Knocking sound. You must have heard, you must have experienced at your home when you are closing the valve in kitchen or bathroom, when you are taking bath or when you are taking drinking water directly from the pipeline in your kitchen. When you stop the valve suddenly, you must have heard dhug dhug noise. That dhug dhug noise is nothing but known as knocking. That is because of the phenomena of water hammer. That's why in case of phenomenon of water hammer, we consider the fluid is compressible. Compressible. We'll stop here. We'll continue in the next class, please. Thank you for watching.